This is lesson 3 of 3 for the remote learning group 7 topic for AQA year 12 chemistry. It's better that you try each task and then review. For some of these, you might want to go away and Google them and try and search out the answers if you're not so sure, or use the textbook that's available online. Now in this, we're going to be looking at some more reactions. We're also going to be looking at the tests for halide ions, which will be familiar from GCSE to many of you, but we are adding to the detail that you needed to remember back in year 11. So, testing for halide ions. We have a method here that you need to remember. We add a centimetre depth of nitric acid, and then we add a centimetre depth of silver nitrate, and note the observations. Now you do need both of those components, and we will talk about why as we go through this video. Taking a look at the results table and what you would expect to see, hopefully remembering from GCSE, if it's something you covered, we will get a white precipitate with chloride ions, a cream precipitate with bromide ions, and a yellow precipitate with iodide ions. I'm actually including here as well the ionic equations, and I'm doing that because this is a particular common question that comes up in A-level papers, where you would be expected to recognise that the white precipitate is silver chloride, cream is silver bromide, and yellow is silver iodide, and we can see the solid state symbol on those, which helps us to recognise that they are indeed precipitates. Now we're going to move on and look at the questions that follow. The nitric acid is added to remove any excess hydroxide or carbonate ions. So what type of reaction is that going to be? Well, if we're thinking of an acid reacting with a hydroxide or a carbonate, I'm hoping the word that springs to mind is neutralisation. Now without this we might make silver carbonate, and this is another problem. It would make a white solid. So why would that be problematic in this test? And what I'm hoping you've recognised from the observations that we've discussed is that chloride ions would give a white precipitate. We would have no way of knowing if it were chloride ions or silver carbonate ions that had led to that white precipitate. And even if it were bromide or iodide, it would almost dilute the colour down of that precipitate. So it would be harder to distinguish between the cream, the yellow and the white. But actually that's a big problem anyway. We stopped at this point at GCSE chemistry, but we have got extra steps. We've got a part 2 to this method. And that's because if you're relying on your own eye to identify, is that white, is it cream, or is that cream, is that yellow, and you cannot guarantee that you would pick the right one. And that's why we move on to the method for part 2. We've kept our precipitates and we add dilute ammonia to each one, shaking carefully. And we note any observations. And what we find is that with chloride ions, the precipitate redissolves, but with the bromide ions and the iodide ions, the cream precipitate and the yellow precipitate, there will be no visible change. So we then go on and add concentrated ammonia. Now it says here, thinking of safety, that would be done in the fume cupboard. Absolutely cannot breathe in those fumes, it's incredibly corrosive. But what you will find is that with bromide ions, the precipitate will redissolve, but with the iodide, there would be no visible change. The precipitate would remain. We don't even bother doing the chloride ions with the conc ammonia because the dilute ammonia has already redissolved it. And what we therefore have is a far more definitive, conclusive test. And that's what the next question is related to. Now, if we're talking about a very binary choice of has the precipitate redissolved or has it not, that is a far more definitive observation than am I seeing white or cream, or am I seeing cream or yellow? Now we're going to move on to look at uses of chlorine, final section of this topic. And we're going to describe how chlorine reacts with water and how it reacts with alkalis. Now there are lots of facts to learn here, as it says. Starting off, quite a common approach to this question where they tell you what's reacting and what's made, and you need to build the equation. And what I'm hoping that you can see is that we will end up with this. Cl2 plus H2O goes to HCl plus HOCl. Now, looking at what's been oxidised and what's been reduced, let's build the equation up again. And let's go through and work out the oxidation states. Chlorine is 0 because that's the oxidation state of an element uncombined. Chlorine is with chlorine here, so it's 0. In water, we have hydrogen as +1 and oxygen as -2. That comes from the rules of redox. Hydrogen is always +1, except in a metal hydride, and oxygen is always -2, except in a peroxide. Moving on to the other side, because H is always +1, except in a metal hydride, the chlorine must be -1 here. Let's move on to the HOCl. Well, we know the H is +1, the O is -2. And from that, we can work out that the chlorine is +1. So we are seeing that the chlorine has been reduced from 0 to -1 in HCl, but it's been oxidised from 0 to +1 in the HOCl. And the name we give to that, where something is both oxidised and reduced in the same reaction, is disproportionation. You simply have to know that word and know what it means. Now, if we move on, what do we mean by the Roman numerals in brackets? Well, we're more familiar with this from transition metals, but it tells us that the chlorine has an oxidation state of +1. We use it where there are variable oxidation states. And you can see it is positive. In the Roman numerals, it will always be a positive charge. Moving on, we have got reactions in swimming pools. Have a go at these, see what you think. And once again, we can work through the equation based on all of the information provided. The chlorine reacts with water to make HCl and O2. Now, that's a very different reaction. It's also not reversible. I need to balance it. So I need to balance my oxygens. I need 2H2O, which now means I need 4HCl. And because of that, I need 2Cl2. Now, why does this mean it would need to be replenished more often? Well, let's go back to that original equation. That should obviously be reversible. And what we see is we are increasing the HCl, so the equilibrium shifts to the left. And that means we're decreasing the yield of the product. Now, bear in mind, the product is what kills the bacteria in the swimming pool. So, the Cl2 needs to be replenished more regularly. And now, finally, we're going to take a look at an alternative method that swimming pool operators use. Now, there is a deliberate error in this equation. Let's see if we can work out what it is. And hopefully, you've recognised that it should be a reversible reaction. But why might this be something that people would rather use than chlorine? The key is in the state symbols, actually. NaClO is a solid. That means it's easier to handle, it's easier to store than chlorine, which is a gas. Now let's take a look at reactions of chlorine with alkali, and we want to know why this is a disproportionation reaction. We've already touched on this earlier in the video, but let's take a look at it again. The chlorine is 0, we've got our sodium, oxygen and hydrogen included there. So in my NaOCl, I know my Na is +1, my O is -2, so my chlorine is +1. In NaCl, if my Na is +1, my Cl is -1. In my H2O, I've got +1 and -2 again. But we can see the chlorine has been oxidised and it has been reduced within the same reaction. And that is the definition of disproportionation. That takes us to the end of this chapter, the end of Group 7. And taking a look, this is helping you to work out where you might go next. We've got keywords. You can ask yourself if you're happy with them, if you're confident with using them. And we've also got some ideas here for what you might do to really reinforce and embed that learning. Thank you very much. Goodbye.